All right. Thank you for the invitation. It's a great pleasure to be here. So I want to talk about two-dimensional topological superconductors. And the idea is to find new ways to invent new topological superconductors because finding it in just the naturally occurring materials seems difficult. So if you want to have a strategy for discovering or designing new topological superconductors, we should have ideas on what are the essential ingredients. So essential ingredient for any superconductivity is, of course, you need charge carriers and you need pairing interaction. But for topological superconductor, there are further conditions. That is, we want to restrict the phase space. The adjective topological is restricting what kind of superconductor we want. So we don't just want superconductor, we want topological superconductor. So what is the topological superconductor? We want to have, let's see if I can get the pointer. Okay. So we need, first of all, odd-parity superconductor, and we want superconductor, such odd-parity superconductor of spinless fermions. And if you can accomplish that, you're expected under conditions such as having vortices or edges, you can have Majorana bound states. So what is my strategy for trying to invent or design new superconductor? I want to target from two different angles. One is targeting the spinlessness of the band structure, that's the kinetic energy part, and attacking the interaction, restricting the phase space in the interaction. So the idea is to get a topological superconductor, we want to restrict phase space. And you can try to do that starting from the kinetic energy in the band structure side, or you can try to do that from the interaction side. So the first strategy is to, let's see, why is it not? Oh, that's working, okay. The first strategy is to try to manipulate the band structure. And in this strategy, I want to talk about two examples. One is groups 6 TMDs, transition metal dichrocollagenide, and surfaces of iron selenide tellurium. You can find details of this group 6 TMDs in this paper, and iron selenide telluride is in this preprint under review with PRL. So spinless fermions, like if you have spinless fermions, their pairing channel is going to be more restricted because the exchange, under exchange, the antisymmetry that we require of the pair wave function is going to cannot be satisfied from the spin channel, so it has to be satisfied in the orbital channel. The idea for generating spinless fermion setting in real space was what's proposed by Fu and Kane, and this was the underneath idea of using topological insulator surface states. And so there, the idea is, okay, you're not having spin polarized fermions, but what matters is to have spinless fermions. So if you use the surface state, you get a spinless fermions, and then if you approximatize and bring in pairing, you can get a topological superconductor. Now, what about achieving this spin splitting or spinlessness in momentum space? In multi-valley systems such as TMDs, with spin orbit interaction, this can be possible. So this is precisely the situation in the valence band of group 6 transition metal dichrocollagenide. These are D electron systems. So, and there is significant spin-orbit coupling. Spin-orbit coupling is of this form, L dot S. And what's happening is that because the valence band has LZ plus minus 1, although conduction band has LZ equal to 0, the valence band experiences very significant splitting due to the spin-orbit coupling. And what's noticeable is that between the two valleys, valley K and K prime, that are related to each other by inversion, because of the system lacks inversion symmetry, they have actually opposite spin splitting. So if you put the chemical potential in this window, you end up in a situation where you have one spin species for one valley and opposite spin species for another valley. You have spin valley locked system. And these systems have already been shown to be superconducting when you dope into the conduction band. As occurring, they are semiconductors. But if you dope it into the conduction band, they show superconductivity even for a single layer system with very high TC for the scale of the system. So the idea is, what if you dope into the valence band and make use of spin valley locking? Now, to pursue this idea, we considered a model that's just consisting of the whole Fermi pockets. So we have one spin up pocket and spin down pocket for the two valleys. And we considered purely repulsive interaction-driven pairing. Now, the fact that the point group symmetry C3V due to the lack of inversion symmetry is important because that low symmetry means the A1, there are only two distinct irreducible representations, and what we typically think of as S wave and F wave will mix, and P wave and D wave will mix. So if the repulsive interaction blocks the S wave channel, it also kind of blocks the F wave channel, which is often the leading channel in trigonal symmetric systems. And the question is, can we make this E channel be preferable when we drive the superconductivity out of purely repulsive interaction? We've investigated this possibility of repulsive interaction-driven pairing using two-step RG, and the formal procedure is to first, in the first step, you go from the largest length scale, largest energy scale, down to the intermediate energy scale, which this is sort of a formal way of thinking how we arrive at a model like this, where you have effective interactions. So this is inter-valley interaction, and this is intra-valley interaction. And then in this stage of going from the highest energy scale to this intermediate energy scale, you're perturbatively deriving how these effective interactions are given in terms of microscopic scales. So microscopic parameters that we have U and the band, the kinetic energy. So this U is entering the effective interaction in this form. So for the inter-valley interaction, these are the two terms. You have to go to two-loop. And the intra-valley interaction, there's only the two-loop term. And to get to that expression, you have to do this kind of diagrammatics. At the end, you find that actually there is attraction in the L equal to 1 channel, although we started with purely repulsive interaction. And this is because of the anisotropy. And then we find the RG flow for this effective interaction parameters. And what you see is that if the bare strength at the beginning was negative, it's going to lead to divergence in the susceptibility. So attraction is found in the P wave channel. Now, there are two P-wave channel possibilities. One is intra-pocket. Actually, the illustration is flipped. Intra-pocket is pairing inside the pocket. So intra-pocket P-wave is this illustration. So pairing inside the pocket means your pair has finite center of mass momentum because they are centered at the valley. So this is going to be a modulated superconductor with a Chern number that can be plus minus 1 for each pocket. If interpocket P wave dominates, one is going to have overall P wave channel with zero center of mass momentum. So this is going to uniform superconductor. To avoid having nodes, then one expects it to be time reversal breaking. And because there are two pockets, this is going to be Chern number 2. So these are two possibilities that we've predicted. And the idea is at the level of this effective theory RG study, one cannot distinguish between the two of these possibilities, intra versus inter. But because inter is finite momentum, it's possible that zero momentum pairing will be favored. But to really tell the difference between the two, one would need to work to go beyond this recoupling RG. But the bottom line is one can make use of this spin valley locking and repulsive interaction-driven pairing to get P-wave superconductor. Now, another very exciting place for the manipulation of the kinetic energy that can lead to topological superconductor is iron selenium telluride surface states. And you can find more details of this work in this preprint. So iron's FESET is a system that have attracted much interest. First, because the iron selenides are superconductors even at a single atomic layer level, but FESET through the doping of tellurium, it was predicted in 2014 that one can turn the band structure of the surface state, band structure topological, and anticipate surface state to manifest the situation that was predicted, proposed for 3D TIs in one system. So the system itself was expected to have both the surface state that is spinless, as well as superconductivity coming from the bulk. Now, because this is a system that is naturally produced, and also the TC, superconducting TC, is high compared to any other topological superconductor candidates. So there have been a lot of excitement, and the natural pursuit was to prove the existence of vortex-bound Majorana mode, zero energy bound states. And there were several groups in Japan and China have pursued STM studies studying the vortex bound states. And for a while, there were issues of reproducing results and contradiction between results of different groups. Some groups found what seems to be quite compelling in zero energy vortex bound states, and other groups found states that seem to be not so much vortex zero Majorana bound states, but something like Caroly-Dujan states. Recently, this is as of last year, different STM groups results started to converge, and simultaneously clarified why there have been contradictions. what this, I think this is still in a preprint state of, from Hai-Hu Wen's group showed, was that magnetic field that is necessary to induce the vortices. When you increase the magnetic field, the fraction of what we call full vortex, which is the vortex with zero bias peak, and the empty vortices without zero bias peak, the fraction was changing with magnetic field. That is, when you increase the magnetic field, fewer smaller fraction of vortices were showing the zero bias peak. So here are examples of looking at two vortices. So in one vortex, in some of the vortices, there is a zero bias peak that shows up when you apply magnetic field, and this zero bias peak persists up to high field. But in other vortices, the zero bias peak that shows up disappears at higher field. So as a result, when you go to higher and higher field, smaller fraction of vortices were exhibiting zero bias peaks. So now the puzzle is, why some vortices are not showing the Majorana bound states or zero bias peaks, and secondly, why are they dying out, right? And obviously the two are coupled questions, and these questions really need to be answered before we can try to make use of this possible topological superconductivity that's just in front of us. So what we studied in this preprint was the possibility of competition between two different topological states for the opportunity presented by the surface state. So we have Dirac surface state. This Dirac surface state without superconductivity in zero field would be a Dirac surface state, but one thing that we had to take into account was the fact that there are iron interstitials. So what we considered was taking the iron interstitials and how they would respond to the magnetic field to be aligned into account. We thought about two possibilities of how the Dirac surface state can be gapped. So the idea is there is this gapless Dirac surface state, and in the presence of magnetic field, there are two ways in which the surface state can be gapped. One is for them to form superconductor and topological superconductor, and the other would be for them to form half quantum anomalous Hall state being influenced by the exchange field. So then what we have envisioned is that on the surface of FE SETE, there will be two different regions, two types of regions that are bordering each other. One is half quantum anomalous Hall, where your Dirac surface state before getting a chance to be a superconductor just got gapped out because of the exchange field. And the other is the superconductivity gapping the Dirac surface state. Now, these are two distinct topological states that can fight for gapped states that can fight for the surface state. And therefore, at the boundary, there will be edge mode. And thinking about that boundary edge mode at once resolves the question of what had happened to the Majorana zero mode that would have been there before half quantum anomalous Hall. That is, the vortex bound state now becomes the edge chiral mode, and the need for there to be an edge state. So this, on the right-hand side, I'm showing you the results of calculation where we did real space Boolean simulations to impose the vortex and with the surface state. So what you're seeing is what one would have in the region of topological superconductor without the exchange field, you have this Majorana bound state. But in the region, when you get to the boundary between the topological superconductor and half quantum anomalous Hall, this state, Majorana bound state that was at the vortex core, now spreads out, gets pushed out, and spreads at the edge of the system. So then the prediction is that can be experimentally tested is that there will be chiral Majorana mode as you pick a pair. If you pick a pair of full vortex, that is vortex with Majorana zero mode, and empty vortex, that is vortex without Majorana zero mode, if you cut across a line with STM tip, you will see that there is the zero bias Majorana zero mode in the full vortex. We knew that's a full vortex, but as you approach the empty vortex, one should detect the edge state. So this is what one would expect as you go from position 1 to 2 to 3 to 4. And on 3, because of the finite size effect, we see kind of a spread out intensity, spread out peak, but this is a peak associated with this chiral Majorana domain wall mode. So let's see. Okay. So these are the strategies that we've thought about in terms of trying to manipulate the band structure, the kinetic energy side of my pairing, with the goal of trying to restrict the phase space of pairing. Now, what about interaction? Can we also try to restrict the phase space of interaction? In this channel, we have thought about several possibilities that are all revolving around the theme of using interface, metal, quantum paramagnet, not necessarily spin-ice, but quantum paramagnet interface. More details of this work is in this paper and recent publication here. Okay, so how do we manipulate interaction? Coulomb interaction is, nature given. Phonon mediated interaction is nature given, and these interactions often are in S-wave channel or isotropic. Now, in the pursuit of non-phononic mechanism, because phonons give us S-wave pairing, what's perhaps best known is the RVB approach, which is, okay, let's start with spin singlets that's just ready to become pairs. They're already paired, just ready to move around coherently, and let them move by adding holes. But it's always proven very difficult to dope quantum spin liquids even if you find them. So the strategy that we have thought about was, instead of trying to destroy quantum spin liquid or quantum paramagnet, let's let it be, but make use of the spin fluctuation in the system. So the proposal is, take your favorite quantum spin liquid or quantum paramagnet and put a layer of metal on top. Then you have two necessary ingredients coming from different materials. You have your charge carriers and you have your interaction. Now, how am I going to change the interaction? Well, I'm going to change the spin liquid that I'm using, and they have anisotropic. If they have anisotropic spin fluctuation, that's going to be reflected in my pairing interaction. And how am I going to treat this complicated system? Well, my scales are naturally organized. There is a natural hierarchy of kinetic energy and the energy scale, magnetic energy scale, and the coupling. So I'm going to do perturbation theory. So this is, in essence, replacing phonon by spin fluctuation and making it come from a different material. Now, this spin fermion model that we used have already been studied for a long time. Without the spin side having the exchange interaction, that would be this Donia phase diagram. You get Kondo singlets through the interface, and the RKK interaction ordering the spin system when it does not have energy scale of its own. Now, when the spin system has energy scale of its own, you can have more complicated phase diagram. And here you still have Kondo singlet across the interface, but now the spin system is interacting and have a quantum fluctuation. Then it could be a RVB singlet in there, and as a result, the itinerant electrons can form Cooper pair. They can all coexist, and that would be a strong coupling limit. What we wanted to study was a weaker coupling limit, where we can use perturbation theory. And what one should predict here is superconductor on the interface or the metallic layer riding on top of the spin liquid in the insulating spin magnetic system. So we wanted to study we would like the metal side to be as simple as possible so that it does not have mechanism of its own. And we want to know the spin system as well as we can. The idea is very simple. Let's take two systems that we know well, and then let's couple them. And if there is superconductivity, we would know what is going on. Now, the system of choice we studied first was SPICE. SPICE is a frustrated pyrochlorous spin system where spins obey what's called the ice rule, just like in water ice. And this constraint can be expressed using a divergence-free condition, like we expect in electromagnetism. And you can anticipate the spin-spin correlation to be of this dipolar form, just following from this constraint. So we studied this system by considering the kinetic energy for the conduction electron and the coupling of the Kondo form, and we integrate out spins and we arrive at effective spin-spin interaction. This is the interaction between itinerant electron spin density that's imprinted from the spin liquid. And we found for the SPICE, because the interaction is this very restricted in the phase space, because of this extreme anisotropy, there is a selection rule that prevents the pairing in the even parity channel. Just like the familiar selection rule, Wigner-Eckhart theorem for hydrogen atom, there is a selection rule at play for this system where the pairing in the even parity is forbidden and only odd parity can occur. And when we studied this a little more carefully, we confirmed all this sort of qualitative intuition-based thinking, and we could proceed as if we're studying electron phonon system, and you get the pairing, the TC, superconducting TC, in a form that looks familiar, except that now this is not the bifrequency, this is the spin energy scale, and this lambda is this dimensionless pairing strength. So now what we wanted to pursue, this was 2017, we've been pursuing possibilities for other paramagnets other than SPICE. And latest material that we've studied is alpha ruthenium chloride, which is pursued as perhaps the most promising leading candidate to manifest the Kitaev model. Now, the material as given by nature orders, it's found in this zigzag order phase. But goal would be to try to bring it towards this Kitaev point. It's already been shown that under magnetic field, the ordering gets suppressed, and there are very tantalizing measurements and also associated debate around it. What we were interested in was, can we, if we use alpha ruthenium chloride as our paramagnet, if we can put a metallic system on top and form a heterostructure, how would that affect the system? And we realized as we wanted to study what would be a good metallic system and what would be the effect of putting a metallic system on top, we realized that actually this is a very open area, virgin area that's not explored, mismatched hetero-interface. If we are to use a van der Waals material like ruthenium chloride, a natural system to consider as a metallic layer would be graphene or other van der Waals systems. Now we're talking about two different van der Waals systems that are mismatched. Their lattice constants are different. And then you cannot use DFT because you cannot, well, you can use DFT with a gigantic supercell. Now, if your mismatch is big, that requires a very big straining of a big supercell. So what we realized was that, well, if there are good ways to study these kind of mismatched heterostructures while the technology for making these are ever progressing, why don't we start somewhere simple? And that somewhere simple is where we studied the mismatched interface theory. So interfaces are interesting. Van der Waals interfaces are very interesting these days because of all the Moray systems. Now, Moray systems are also example of non-crystalline interface, but without necessarily having twist angle, when you form these kind of mismatched interfaces, the problem becomes difficult. And when you don't even have a superlattice, like in Moray, it becomes particularly difficult. So that's what we've studied. How much time do I have left? Is there organizer, chairperson?
Yes, I think you don't need to worry much about your remaining time. Please
Oh.
go ahead. Yeah. If it's not too long. Sorry, I haven't
What is the
counted actually.
definition of that? What is the definition of not too long? What if I go on for hours? No, I'm not going to go on for hours, but 10 minutes, right? 10 minutes?
How long do you think you need?
Let's see. Let me see. I think 5 minutes.
5 minutes?
Can I have
Okay.
five?
Yeah,
Yeah,
sure. Please go ahead.
5 minutes.
Thank you.
Okay. All right. Okay. So, I was rushing, so let's step back a little bit. So, as we pursue this desire, we want to make use of alpha ruthenium chloride to do something exotic like making a superconductor. We need to be able to form a heterostructure and study the heterostructure. We found this obstacle that, hey, people don't know how to do this, how to do a calculation with it. So my group teamed up with ab initio expert colleague Thomas Arias, and three of us studied how should one describe mismatched interfaces. We invented an acronym MINT, which is short for Mismatched Interface Theory, and it's a two-step procedure. The first step is to construct what we call MINT representation of the heterostructure. So what we do is we form a small cluster of one of the systems. That's this MINT representation cluster C. And we let it move around on the other system. So in this case, you can choose whether you do MINT representation or cluster of carbons or cluster of ruthenium chloride. In the illustration, we have cluster of carbons. So you put a small flake, small cluster of one system, say carbon, on top of the ruthenium chloride, and we can average over its positions, let it move around, and we place them in a supercell where the distance between the flakes is far enough that they won't affect each other. Now we have a system that can be just plugged into the typical DFT setting machinery. So we study the system using DFT, and then we can study these electronic properties of that system. But we then do systematically increase the flake size to see how quickly we can reach what would be the setting when both systems are macroscopic. The idea is when you have mismatched system, if you go around the whole system, the registry would be averaging over all possibilities. So by studying reasonably sized flakes, our hope was that we should be able to mimic the macroscopic setting. And indeed, we found the moment our carbon flake here reaches one benzene ring, to get a graphene, I need to have a lot of benzene rings. But the moment I reach one benzene ring, I approach the charge transfer that is very close to what we find in subsequent larger flakes. So there's a sense of convergence. And we can scale these predictions from these flakes to extrapolate to the macroscopic setting. And what we predicted from this is that when you form a graphene alpha ruthenium chloride heterostructure, there will be charge transfer. With the predicted amount, which means now my alpha ruthenium, the graphene is losing charge to alpha ruthenium chloride. The graphene gets hole doped, alpha ruthenium chloride gets electron doped. So one would achieve the doping that one had been wanting on a quantum spin liquid. Moreover, when you change the charge carrier density, that also changes the effective interaction. So what we were able to predict from this is that the interaction parameters get changed from as grown alpha ruthenium chloride to be much closer to the Kitaev point target. Now, our referee said these are great ideas, but in reality, the complications of material will get in your way. Now, so we've collaborated with the reality. We worked together with Eric Henriksen and Ken Birch, and what we found was that MINT predictions actually can predict accurately the doping that can be achieved using alpha ruthenium chloride as an acceptor. So alpha ruthenium chloride accepts electrons from many different van der Waals materials. Here we studied monolayer graphene, bilayer graphene, and we placed graphene on different angles on alpha ruthenium chloride and studied the angle dependence of twist angle dependence of the doping and the dependence on mono, bi, and other material. And the estimate of the doping from the experimental approaches like Raman and transport is very much consistent with what MINT could predict. What would be really fascinating is to study what's happening to ruthenium chloride in these heterostructures, which has not been done yet, but you can find more details in this paper when it comes to the probing on the graphene side. So on that note, let me finish. I've talked about different designing strategies for 2D topological superconductors. One is to try to target spinless fermion rail for the kinetic energy, and the other is to try to make use of magnetic fluctuations, like as if just like we would use phonons, but by forming a heterostructure, we can pick and choose what we want to put together. It's kind of like going to a salad bar. Now, it's easy for a theorist like me to pick and choose. It's much harder for these materials to come together, but we have some collaboration in the works that are giving very promising signs. So I think perhaps some of these kind of dreams can actually come true. And on that note, thank you for your attention.